Let me learn about topic 2 in your unit 4 is latches in today's session. So the basic difference between a latch and a flip-flop is latches comes under your asynchronous sequential circuits, where flip-flops comes under your synchronous sequential circuit. In last class we discussed about the difference between the synchronous sequential and asynchronous sequential circuits, where in synchronous sequential there is a control signal which can control the operation of your flip-flops or your sequential circuit, whereas your asynchronous sequential circuit are those which cannot be controlled, where your outputs or the next states depends on your present inputs as well as on your past history or your past outputs. No control signal is used in asynchronous sequential circuit. In latches, so latches and flip-flops, those two are used to store one bit of data. So hence, it's a storage element which can hold one bit of data. So either a 0 or it is a 1. So latches are level sensitive devices, so which means it is sensitive to the changes in its inputs. So hence, if you change any input out of the n number of inputs, so since here I have two inputs, if I change any input, that may affect your output of the sequential circuit. So they are sensitive to the logical levels on your input. So it's a digital circuit where the logical levels are only two. We have either a logical 1, a high, or logical 0, which is a low level. So now any changes in your external inputs can affect your output of the sequential circuit. So this latch are sensitive to the applied inputs. So hence here no control signal is used. Let me learn how it is constructed using your NAND gates. So I used here two NAND gates which can function like a NOT gate, and we have been connected two inputs A1 and A2. So these two gates are acting like a NOT gates. Now, so let us assume your state of the circuit is 0. So if Q is 0 is your present state or the output, so which I consider as a present state or your present output is 0. Due to this 0, so as here connected, that output as your inputs of your G2, output of G2 is connected as your input of your G1. So now since Q is 0, A2 input becomes 0. When A2 becomes 0, so the inputs which are connected on your G2 become logical 0. So NAND truth table is, so if any input is 0, output of your NAND gate become logic 1. So this is your truth table of your NAND gate. So if any input is 0, output of your NAND gate become logical 1. If all inputs are 1, output of your NAND gate is 0. So now if both inputs are 0, G2 become 1. So earlier it is also equal to 1. Now it is also equal to next state is 1. So hence this 1 is applied on your A1. So as a A1 on your G1, gate 1. So since you have two inputs are 1, so output become next state is now, this is your present state. Now it will move to your next state as your 0, since both inputs, so available inputs on J1 is 2, those two inputs are logical ones, so hence NAND gate output will give you, first NAND gate output will give you 0. So it will restore the 0 again, which is a present input, present state is 0, so this will restore your 0. So if I treat logical 1 as my present state, now that 1 is applied as A2. So since two inputs are 1, 1, so now this will change its state to 0, and this 0 is applied as A1. So hence if the two inputs are zeros, so your gate output is 1. So in first case we assume present state 0. So which restored as your next state is also equal to 0. The second case, we assume the present state is 1. Again it is restored as a 1. And there is no external inputs which are connected to control the operation or to change its state from either from 0 to 1 or from 1 to 0. So 0 to 1 means set state, it is called, and 1 to 0 means it is called reset state. It holds a logical 1 bit, either a 1 or 0. So in the two cases it only restores the previous states. So there was no external inputs are connected, hence it restoring the previous states as your next state. But in order to have a set state or a reset state, let me connect the external inputs on this NAND gates. So then that become the SR latch. So if set input is enabled, so then it has to move its state from 0 to 1. So which can hold the logical 1. If reset input is enabled, it has to reset the state of the flip-flop to logical 0 based on your external inputs. So let me modify this simple circuit with your two NAND gates. Now instead of taking the first NAND gate and second NAND gate as your NOT gates, so let me take the external inputs as set input and reset input, and one more input you have on both two NAND gates which are transferred from your present state as your second input to the second NAND gate, and complemented output state has been acting like a one of the input on your first NAND gate. So now upon connecting this, so now if any changes in your signal level or the external input, so that can cause the state transition from 0 to 1 or 1 to 0. So hence those are called as set or reset latches. Now let us first assume set input is 0 and reset input is 0. If both inputs are 0, 0, so here your present state is 0 or 1, your next state, since set input is 0, it become 1. Here, so your complementary state is 1 or 0, this gate output is also becoming logical 1, since R become 1, R become equal to 0. So NAND, we know already the NAND logic, any input 0, output of your NAND is logic 1, output of NAND is logical 1. So if one of my input is 0, so both complemented state and your uncomplemented states become logical ones. So it's not following the complement law, because it's a sequential circuits are the examples of digital circuit. Digital circuits are developed using your Boolean algebra, and it is not obeying that NOT or your complementation law. So hence, so this state when S0 R0, your next state which is Q1 plus 1 and complemented state Q1 plus 1, because so both become logic ones, so those are treated as your forbidden state or invalid state. So we define these states as your invalid states upon applying your S input R input with a 0. So you would obtain all both complemented state and uncomplemented state. Now it becomes logical 1. So now, so let me move to your next input condition. If S input is 0, R input is equal to 1. So since the set input is 0, so this first NAND gate output, present state is 0 or 1, next state become logic 1. And that one is transferred as your one of the input to the second NAND gate. So since that, so your complemented state is 1 or 0, it will transfer to the logical 0. And this 0 if it transfer, so you obtain your set state. So 0, 1. The next state Q1 plus 1 is equal to 1 and your complemented state is equal to 0. So since that this state definition is set state and the above state is defined as your forbidden state or the invalid state. Next, if my inputs are 1, 0, set input is 1, reset input is 0. In such cases, so if it is 0 or 1, so then your reset input, since it is 0, now in this case your reset input is 0. When reset input is 0, your second NAND gate output will transfer from either it is 0 to 1 or 1 to 0. So it will transfer to logical 1. Complemented state is transferred to logical 1. S input 1 and the forwarded complemented state is 1. So since that both inputs are 1, this output becomes 0. So next state is 0. So if reset input is 0, second NAND gate output become logic 1, where present state is 0 or 1. Since that, so this is transferred as second input. So already set input is 1. So if both inputs are 1, your present state is 1 or 0, your next state is a reset state. Next, if I apply both inputs are 1, 1. When both inputs are 1, 1, so then here, if both inputs are 1, 1 here, so now I need to assume if my present state is 0, complementary state is 1. So this 0 is transferred to the second NAND gate. So since one of the input is 0, so complementary state become logic 1 and that one is transferred as your input of your first NAND gate. Both inputs are logic 1, hence you obtain your logical 0. So earlier your present state is 0. Now your next state Qn plus 1 is your next state. How to define the next state is, so after an instant of time, so after transferring the external input, the new state is called as your next state. So which is denoted as Qn plus 1, or we can define that as a next state. So next state becomes 0. Earlier state is also present state is 0. So and now the state may not change. So which is restored again as your 0. So it is same as like your present state, which is Qn only. Qn 0, Qn plus 1 is also equal to 0. Now if I assume Qn is S input, R input or 1. So for 0 you got 0. For 1, so Q bar is 0. So this one is transferred as your input of second NAND gate, and now since both inputs are 1, 1, so complemented state becomes 0 and that complemented state is applied as your first NAND gate output. Any input 0, output of your NAND gate become logic 1. So present state is logic 1 earlier. Now upon transferring the inputs or changing the level on your external inputs logical 1, you obtain the same state as your next state. Present state as your next state, which is again logic 1. Hence there was no changes in your output if S and R inputs are logic 1. So it continues its present state as your next step. You can also construct a NOR latch using your universal gates NOR. It's just replacing your NAND gates with your NOR gates, and here we shuffle your inputs. Position of S is replaced with R, position of your R is replaced with S. Now upon connecting the feedback, so since it is doesn't have clock signal, it comes under asynchronous sequential circuit. Now let me analyze this circuit by transferring your signal levels on your inputs. So first let me learn, so what is the basic logic of your NOR. So NOR can give you the logical 1 output if all inputs are 0. and if any input is 1, output of NOR gate become 0. Output of NOR is 0. So now, so let us first transfer S in R inputs are 0, 0. If both are zeros, we can't define the output. So let us assume my present state is 0, complemented state is 1. So this 0 will comes as an input. Since S input 0, here the complemented next state is equal to 1. Since you have two inputs on your NOR gate, both are zeros. So if all the inputs are 0, output of NOR is 1. And that 1 is transferred as the input of this. So hence your output is 0. So for 0 you got 0 as your next state. If it is 1, so 1 is transferred on this. So hence any input is 1. So output of this Q bar become logical 0. And this 0 is transferred here as the one of the inputs. So if both inputs are 0, next state of your NOR latch is 1. So in your NAND latch we obtained the next state as your present state is on your SR inputs are 1s, but as in NOR latch we obtain so the same state, no change state when S and R inputs are 0, 0. So hence it continues its present state as your next step. So if S input and R inputs are 0, 1. So S input is 0, R input is 1. So now any input is 0, your present state is 0 or 1. Output of this NOR gate will give you 0 and that 0 is transferred, so Q bar will become 1, complemented state. So hence present state, so set input is 0, it will, or R input is 0, it will reset your flip-flop. Next, if my inputs on your set input and reset inputs are 1, 0, so here S input is 1 and reset input is 0. Since of this, so present state is 0 or 1, so complement state must be 1 or 0. Since one of the input is 1 on your set input on your NOR gate, so since that, so this become logical 0, complemented state. So in complemented state, if it is applied on this, so if all inputs are 0, so output of NOR gate become logic 1. So hence here 1, 0 sets your flip-flop and 0, 1 resets your latch. If 1, 1 are the inputs, if R is also equal to 1, so no need to transfer this because we don't require that second input since one of the input is logic 1. So Q become logic 0, Q bar is also equal to logic 0. So if Q and Q bar are both are 0, which is not obeying complementation law, so hence these are known to be the invalid state. So here, so active high input resets your flip-flop, active high input on your set which will set your flip-flop. Hence, these latches are known to be the active high input latch, whereas the previous one, which is NAND latch, is an active low input latch. So since the low level on your S input can set your flip-flop and low voltage level on your reset can reset your flip-flop. So these are NAND latches are known to be the active low input latch, where your SR latch with NOR gates are known to be the active high input. So this is our session about your latches. In next class we are going to learn about the flip-flops.